Hi. So in English, I just FYI, I go by Greg. And so this is it's kind of like I'm very happy. It's like kind of like a U-shaped journey because I just finished my PhD here in the CBL and in engineering, and I'm at Imperial. I'm a postdoc there, and I'm back in the math department. So you cannot keep me away from Cambridge. Okay. So this work, it's about stuff that I did at an internship at Google. So I was working there on the Google Translate team. And so this work here is about sort of like a sort of a serendipitous coincidence. So they had a lot more experience, obviously, on language models. And this, so they were working with some translation. And I had an information theory background, and it turns out that this language modeling area in machine learning is a little bit of an alchemy. It's kind of like alchemy at the moment. People just do stuff and see what sticks, and they maybe sometimes try to chase ideals that are impossible to achieve. And so this talk is about kind of one case study of this occurrence. So people were doing something silly, and I came in and I showed them that maybe it's hopeless. So this is a very negative presentation. So hopefully you're all cheery. But okay, so and yes, I should say that this work is. how good the translation is. So basically, what I said, okay, is that they predict MQM scores, but I just told you that MQM is not a score based. So where do we get the scores from? So remember that I showed you this big table of different types of errors. What people do is they take those error categories and they put them into major, minor, and neutral errors. And depending on whether in the MQM rating it's a major error, minor error, neutral, we assign a numeric value to it. Okay, is this clear how this data is collected? So we have like this big data set of source text, target text, and then we also have the ratings produced by the MQM raters. So we have the very detailed quantitative descriptions, and now we're going to take that quantitative description and going to turn that into a score for each translation, and then train a big, like we'll fine-tune a large language model to predict these scores. Okay. So the neat thing is that these are now these neural metrics. They are now much less sensitive to this problem of, okay, if two things are close in meaning, then they will get usually a very similar score. Okay, so this is what people. This is now the state of the art. Yeah. So I think metric X is based on. It's either based on the 8 billion Gemma model, or it's based on maybe Llama. I can't remember, but it's basically like on the order of, yeah, exactly. It's over 1 billion parameters language models. They have, like, as you might imagine, 1 million versions as well. I can't remember what we used exactly for our experiments. I mean, I know the version number of the metric, but I don't know what's underneath. What language model is underneath? Okay. Okay, sorry. So this is the setup. Okay. So we want to assess accuracy. We want to assess naturalness, and then this is what people do. So we want to do automated assessment. We have the classic metrics like BLEU and Charef, which are basically like MSE. We have the neural metrics, which jointly assess. They try to jointly assess accuracy and naturalness, and they use these crazy LLMs. Okay, but so this is what people do. Okay, so their hope is that they're going to use neural metrics to jointly do this assessment. They want a single score assessment. Okay, and say, okay, this system is this good. Okay, so now for a half-minute break, just to explain the paper title and then the talk title. You can't feed two birds with one score. So I hope everyone here knows that this is a scone, and the pun doesn't work in British English. So it's feeding two birds with one scone. And so my boss decided to change the M to an R, and then you can't feed two birds with one score. And if it's not clear, this is a more graceful alternative to killing two birds with one stone, which we didn't want to put in the paper title. But so that's why this is called this. Okay, but so the question that we asked in my internship is, should we assess accuracy and naturalness jointly? So is this idea of using neural metrics to get a single score summary of a system's performance okay or not? And the starting point was these results. So there's this workshop on machine translation, WMT, a workshop on machine translation. And so here they have challenges. And what the challenge is, they just release a source, like a corpus in some source language, like English or Spanish or Japanese or whatever. And then they say, okay, this is the target language. Now everyone can submit systems that translate this corpus from one language to the next. And then they take the translations produced by these candidate systems, these competitors, and then they rank them. First, they rank them with this auto-rank score. And what this auto-rank score is is it's a combination of metric X and commits. So it's some, like, I don't think it's released publicly like how exactly it's weighted, but it's basically they compute some metric X score, some commit score, and they average them somehow. And then they rank the systems, and the top 10 or top 20 systems, they also then do a human evaluation, and they check which systems of the top 20, let's say, do the humans prefer. And so for multiple years in a row, what people are seeing, this is like baffling the community, is that the system that wins in auto-rank, so according to the automatic metric, is not the one that wins the human evaluation. Yes, sorry, exactly. So one, like here, Unbabble is the absolute winner. Whereas it seems like, and for the humans, larger is better. I'm not exactly sure. All right, so these are MQM scores, which is an error score. So you want to negate it, and that's a goodness score. But so yeah, so GPT-4 won last year, but it wasn't the winner in autorank. So what the hell is happening? Okay, and so our paper seeks to sort of explain, give some theoretical explanation of why this occurs. Okay. Okay. No signal. Some signal, please. Okay. That's not the signal I wanted. Okay. Okay, so where we were is that there's no formal notion of accuracy and naturalness. And so therefore their interaction is not very well understood, and the community is a single score assessment. So this is the state of the nation. Okay, but we have this silly thing that the results don't seem to align with the human evaluations. Okay, so why is this? And so it turns out that information theory is the answer. Okay, so it turns out that some people, in particular Blau and Micheli, in 2016, have kind of already figured something very similar out in the image reconstruction domain. And it's called the distortion perception trade-off. So if you know what that is, then this talk is about the distortion perception trade-off in translation. But so basically the idea in our paper is to identify this notion of accuracy of a translation with some generalized notion of distortion, and naturalness with the notion of realism or distinguishability. Okay, so again, to recap now a little bit more formal in the ingredients, so we will need a source sentence that I'm going to denote by X, a translation system that is, again, going to be a conditional distribution Y given X. Okay, and so what we're going to have is we're going to have reference translation. So this I'm going to make explicitly human. This is actually not needed for the theory, but it's maybe easier to imagine how this would work. So the human takes some source sentence X and produces some reference translation. And then we'll get candidate hypotheses from some candidate system. Okay, so for
how are this X and Y presented
these are the no. Well, I mean, I guess technically, so in all our experiments we use this tokenized text. So X is some tokenized text, and Y is some tokenized text. So if like you can just think of them as just strings of some finite length, like they're kept at maybe, I can't remember how big the context windows of these models are, like maybe. Yeah, exactly. I mean, you should literally think of, I give you like a sentence X, and now these distributions, they are distributions over strings. Technically, if we were to really dive deep into it, then their technical distributions were prefix strings, because every sentence has an end of sentence token. So then we can technically define this over like you can go into like coding theory, and then you can say, okay, like take like some binary tree of strings. But sorry, I don't know if I'm like now veering off on a tangent. And am I answering your question or no?
Yeah, I mean, just I want to know. I mean, it's like the whole sentence you represent in terms of a string, right?
That's right. Yeah, exactly.
That includes the spaces in between.
Yeah, exactly. In particular, like I should say that I keep saying sentence. I don't exactly. I keep saying sentence. Like these could be entire paragraphs or even like entire pages of text. Like this can be whatever that fits into the input and output of a large language model or translation system. But yeah, these are literally just strings. So this is as like these representations in practice are as crude as you can maybe imagine. Like they're just tokenized text. Yeah, is that fine? Okay, cool. So for accuracy, we'll need a generalized notion of distortion. So here, like usually a distortion, you can kind of think of it as a metric. So it has two inputs from the same space. But actually for translation, it makes more sense to include a third argument from the source language. So actually, if you think about it, so okay, by the way, so the classic metrics, like Blue and Charef that I said, okay, these are like the MSc of natural language processing. They are true like distortions in the information theory sense because they don't take the source sentence. They just take the reference and the candidate and then they give you a score. Neural metrics, there are some, so there's some versions of metric X that take all three. And then there's also these so-called quality estimation metrics, which is a dumb name, but whatever, which now omit the human reference. So they're really assessing what you intuitively as a human would want to assess, which is just purely the relation between the source and the candidate translation. Okay, but so in practice, in automatic translation assessment, this is the most general formulation that is used. So neural metrics usually take all three. Okay, and so then the accuracy, like now, but we're back to information theory, then we're going to say, okay, well, the accuracy should be the average negative distortion. Why negative is because distortion is measuring inaccuracy. So we're just going to negate it so that people can think of it easier. And here, what we have, as I promised, so here, this joint distribution XY represents our data set that we collected. So X is like the corpus of source text, and Y here is the human reference translation. And then inside we have the expectation. We're averaging over the translations produced by the translation system. And so negating that gives us the accuracy of translation system Q. Okay, so it's the average distortion in the most sensible way. Okay, hopefully that's not controversial. What might now be a little bit more controversial is the notion of naturalness. And so, as I said, I'm going to try to define it through this notion of distinguishability. So to give you some intuition, I mean, this is maybe easier in a room with slightly more people, but so here are two images. One of them, both of them I sampled from a data set of photorealistic images, but one of them I compressed and then decompressed. Raise your hand if you think that the compressed image is the right one. Sorry, how? Yes, okay, sorry, you're right. Okay, I need to switch it in my head. So, okay, you voted for this one is the compressed image. Anybody for the left image? Okay, yeah, so you had an easy time distinguishing which one was it. Okay, for these ones. Who thinks right? Who thinks left? Sorry, did I not give enough time for the right people? Okay, usually a third option is not available, but we had 2 votes for. I'm going to assume that the other 4 of you voted right. Actually, it's this one is the generated image. But so it's the point is, maybe now it's a bit harder. So the idea is that if the distributions of these images are closer, then it becomes harder to distinguish them. And so this is kind of like the underlying idea of naturalness and distinguishability, that regardless of the source, what we care about comparing purely the outputs. Okay, so naturalness should be a property of the outputs purely, regardless of the input. So yeah, so the idea is to identify the notion of naturalness with distinguishability. So what we do is we pick a reference distribution, okay? A reference distribution over Y. So the subscript just indicates that it's a distribution over Y space. So this could be maybe, you know, if I'm translating from English to German, it could be like just a big corpus of German, of purely monolingual German text. Maybe I look at the European Parliament proceedings and like some German news sources and whatever, and I compile them into a big data set, and that's going to be my R sub Y. And then I'm going to carry out the following experiment, which is slightly different from the intuitive experiment that I showed you. So this is the experiment. The experiment is the experimenter, they draw one sample from the reference. But what they also do is they take their, so this is in the target language, right? This is Y. But they also draw randomly a sentence in the source language from the source corpus. And then they take the system that they want to assess and they have it translated. Okay, they translate this source sentence. So now they have Y0 and Y1. Okay, one of them is a translated sentence, the other one is like a reference sentence in the target language. And now they flip a fair coin, and however it lands, they give either Y1 or Y0 to the observer, and now the observer's job is, given YB, they have to say which way the coin landed, so they have to say whether it was a reference or not, a reference sentence or not. Okay? And so when we're assessing naturalness, we'll be interested in assessing the ability of the optimal observer, like the one who, you know, they can do whatever crazy reasoning to figure out or and detect whether it was a reference or not. Okay, but this is the underlying experiment. Okay, so just to get a little bit more ingredients up, so we have the translation marginal Q. So if I take a translation system, which is a conditional distribution Q of Y given X, then the translation marginal is if I randomly draw a source sentence, what is, and I translate that one, what is the marginal of that? That is Q sub Y. And then I claim that distinguishability is equivalent to a statistical distance between this translation marginal and the reference distribution that I picked. Okay, and again, because the statistical distance is measuring unnaturalness, naturalness I'm going to define as the negated distortion. Okay, so what I haven't told you is how this equivalence holds. So to give you an idea, this is not the only way that you can do it, but this is one that I quite like. So for shorthand, I'm going to denote the P expectation of a measurable function f as just P of f. And then we have these things called integral probability metrics. Okay, so what are those? So I pick two distributions Q and P, and I pick a function class curly f. Okay, and like how big this function class is, it kind of defines the power of my observer. Like the more functions I put in here, the more powerful my classifier is. Why? Because the integral probability metric is defined as the maximum absolute mean separation of these distributions. So I take the Q expectation of some function f and the P expectation of some function f, and I try to push these apart as much as possible. Another way of looking at it, if it makes sense, so it obviously doesn't always make sense, but we might sometimes be able to define, so if I can turn the supremum to a maximum, then I can look at what the argmax is. And so then this f star is the function in this function class that achieves the maximum mean separation. And then I can just think of the integral probability metric as this optimal critic that finds the biggest mean separation between these distributions. So if you're not familiar with integral probability metrics very intimately, So just to give you some examples, so if I pick curly f to be the set of bounded measurable functions over the sample space, that's total variation. If I pick curly f to be one Lipschitz functions, then I get Wasserstein distance. If I pick curly f to be a unit ball in some RKHS, which is a reproducing kernel Hilbert space, then it turns into maximum mean discrepancy, these integral probability metrics. Okay, so we can recover some fairly popular metrics. Okay, but so these are what I'm going to run with for the moment, so integral probability metrics. And so what is this equivalence? So I need to set this, so this is the probability of B landing head, so in this case it will be 1/2. And then I set my, I'm just going to set my loss function as such. So depending on the coin and depending on my prediction, I'm just going to set my loss function to this. The details don't really matter. I just want to show you that if we now look at the risk, the expected risk of the best classifier, right? So I'm averaging over my coins and my samples, and then I'm going to try to pick the f that minimizes this. You can show without too much effort that it's actually equal to a negative integral probability metric over the same function class, okay? So this is just to say that this notion of distinguishability and this notion of statistical distances, they correspond to each other as such. There are other similar results for other stuff like F divergences as well. Okay, so given this, we can now ask the very important question. So we've, did all this work. Was it all in vain? Are they actually, are our notions of accuracy and naturalness the same? If they are, then we worked kind of for nothing. Thankfully, we haven't. So the first question that we can ask is it true that perfect naturalness implies perfect accuracy? So if I have a perfectly natural system, is it also perfectly accurate? So coming up with a counterexample is very easy, because what we do is we just take the reference distribution and we say that we come up with the following very dumb translation system. It gets an input, and then this translation system just ignores whatever input it received, and it just randomly outputs a sample from the reference distribution Ry. And in this case, any sensible statistical distance is just going to be measuring the distance between the distribution itself, and so it's going to be 0, so it's going to be perfect natural, and it's maybe not too difficult to see that it's not going to be perfectly accurate. Now, the question of does perfect accuracy imply perfect naturalness? This is a bit more involved, and so I will actually skip telling you about how it is. But so you can prove theorems in specific circumstances that, so originally in Blau and Micheli's setup, they can prove a theorem that no, it does not imply it, and in our setup, it also doesn't imply it. We can talk about what these things are later. I just want to show you some actual curves. Okay, but so if they're not the same, then there must be some trade-off. So how can we quantify the trade-off? We define the accuracy-naturalness function. And so what is that? For some level of naturalness n, we're going to try to maximize the accuracy of our translation system, subject to the constraint that it also has, at least some, it satisfies some level of naturalness. Okay, and the accuracy-naturalness function is the absolute best translation system that we can obtain. According to this. And so you can show, sort of maybe unsurprisingly, hopefully, that this function is non-increasing. So as I increase the naturalness of the naturalness requirement, the accuracy must the optimal accuracy must drop. And actually also you can show that if this statistical distance is convex in its first slot, then AN must be concave. So it really curves down towards the end. So this really means that towards, if we, like at some point, a small gain in accuracy will cost you a lot of naturalness and vice versa. That's kind of what this means. Okay, so this is the theory part. So now I'm going to show you some curves and points. So first, the idea is, okay, I gave you all this theory, but what does the curve actually look like? So actually computing this curve, as you might imagine, is very, very hard. So we're going to approximate it. And so the way we approximate it is, what we did is we took our source corpus, and we had a large language model. It was some version of Gemini to produce 1,000 possible translations for each sentence. Okay, so here for each sentence we're getting 1,000 possible translations. And then we used another LLM. It was the Gemma 2 billion parameter model to evaluate the Lagrange dual of this objective on each sentence. Okay? And what we did is then we picked the sentence of the at each. So okay, so here we have one parameter that we can vary. We can set different levels of naturalness. So for each level of naturalness, right, we want to compute the curve. So for each level of naturalness, we picked the translation of these 1,000 translations that had the best score at that level. So just to be maybe very clear, I hope I'm not being too unclear, but what I mean by the Lagrange dual is that what I write down for this guy, so it's a one-shot Lagrange dual even. So I have reference candidate, and then minus lambda times, and here we put some naturalness score of the candidate. Okay, and so what is it in our case? It's going to be some log probabilities produced by the model, and for each of the 1,000 translations, for some level lambda, we picked the one that had the best score of the 1,000, and we averaged across sentences at that level. Okay, so there's already going to be a question. Okay, I'm saying, okay, we're doing this like single score assessments. That's not a statistical distance. How does this make sense? We're going to get to that. But so just to show you the curve finally, we translated the okay, so we translated a whole data set of points, and then we average across different levels. This is what the curve looks like. Okay. So again, here we were cranking up the naturalness. So as you can see, as the accuracy increases, the naturalness decreases with it. And so just to give you an idea of like what sentences the language model prefers. So if we look at the English to German sentence, "I've wanted to fly since I was a child," here at the very accurate end of the spectrum, the translation that the system preferred was "Ich wollte schon als Kind fliegen," which is literally, I don't know if you speak German, but it's literally a mirror translation of this sentence. Whereas you can see that as we say, okay, be more natural, and we're fine tolerating a little bit of inaccuracy, then it can go like really kind of poetic. Like this is, oh yeah, like I have always dreamt of flying when I was little. So farther down, we can really see that I mean, of course, this naturalness again is defined by what we pick. So here we picked this large language model to score our translations. If we swapped it out for something else, we would, of course, get something different. Okay, so this is what the curves look like after many approximations. This is kind of the approximation that you is maybe the crudest one that you can come up with that is at least tractable. So that's what we did. Okay, so this is an approximation of the curve, but another thing that you can do now is you can look at state-of-the-art translation systems and ask, okay, how do these fare up? And so this is what it looks like. So just to be clear again, on the left, we have CHARF, so it's this like MSc of NLP. It's like a pure, accuracy metric. And here we have COMET, which is this neural metric. And so what you can see, can I actually laser? Okay, I can't. What you can see is just behind me. Oh my God, I have a bamboo stick. Oh my God, I feel so much more powerful. But so here, a couple of things. So first, it might look like, okay, here there's still like a very big gap, so there's still a lot to go. But so actually, we don't believe this. And that is because you can show by a very simple application of Jensen's inequality that our approximation is overly optimistic. So the curve is always going to lie above the actual true curve. And we believe here that the gap between the true curve and our approximation is very severe. So actually, we really believe that the curve is somewhere here, but maybe our approximation is quite loose. In the case of COMET, it's maybe a little bit more believable, but we also don't believe that the curve should be this high up. So maybe we think that the true curve should be somewhere here. But here we can really see this trade-off that I showed. I started this slide. I started with this slide that this guy is this unbabble model. This is the one that won the auto rank, the automatic metric in the evaluation. And you can see it was clearly optimized for this neural metric because it is really like by a large gap the best model according to this accuracy metric. But then you can see that there are some other measures. I remember a little bit. Oh. Hello, damn. Sorry about this. I don't know why it keeps going to sleep. Anyhow, but you can see. So this is the point that like you can really see that the picture is maybe a little bit more complicated than if you just looked at let's just score models according to a single metric. Okay, and the important message, which I guess, so this is the important message to the translation community, which I realize you're not, is that people think they have this like very strongly held belief that all you need to do is just optimize one metric. And because this accuracy naturalness function is non-increasing, it means that at some point accuracy and naturalness must start anti-correlating. So if you keep optimizing one, then you will lose in the other. Okay, and so just to give you an idea, so okay, the trade-off exists in all languages, and it's interesting to see how much of a trade-off there is. So these scores are now scores that are purely derived from this MQM evaluation. So these are neither of these are they are both of human origin, right? Neither of these are automatic metrics, and you can see that here we have our the trade-off that we saw from the WMT results. So unbabble tower, okay, it sits somewhere in the middle, but then we have GPT, and then there's this other model dot former that they're all Pareto optimal among this set of points. So the picture is more complicated is the point. Similarly, you see the same for English to Spanish and Japanese to Chinese. Interestingly, the hard and sort of maybe unsurprisingly, the farther apart the languages are, the more severe the trade-off. So English to Spanish is basically called like a solved problem, because you can see that the best systems, they're close to like 0 error and like, yeah, exactly, like 0 adequacy error and 0 fluency error. So it's basically almost perfect. In English to German, the trade-off is more severe. In English to Chinese, the trade-off is also a little bit more severe. Okay. So there's one more slide to go. And that is to return to this question that I was saying with the scoring to generate these curves. So ideally, we'd be assessing the outputs of the output distributions of our systems. Now, that's very difficult to do. So what people do is they resort to these single score assessments. So as I said, like we were looking at these language model log perplexities, and then we just averaged these scores. And so then the question is, so how can we relate this to some statistical distance? And I want to argue that, you know, via some very rough approximation you can. And so how does that look like? So that's just the definition of an IPM. Now, I should say that if we just compute some single score assessments and we average them, that's clearly not an IPM. Why? It's because the single score assessment is fixed before the assessment. However, in an integral probability metric, the optimal critic, it depends on the distribution that we're trying to assess. So clearly, what I have clearly this single score assessment is not an IPM. But what is it then? And so the idea is to change the divergence or the distance. And the idea is to average instead of maximizing. So if you squint, then close enough, then an IPM looks like an infinity metric over an appropriate space. And it turns out that, you know, if you modify the right things, then you can define a whole class of p-norms on the same space. So here, what I'm going to do is I'm going to introduce one final ingredient, and that is a stochastic process over critics. So I'm going to call that curly p. And then I'm just going to average. So I'm going to swap out the supremum for averaging over my distributions, and I'm going to do the standard p-norm stuff. And you can show that basically under the very same conditions under which that you put on a function class for an integral probability metric to be a proper metric, roughly the same conditions are required for this distance to constitute. It's always a semi-metric, but under some conditions it's also a proper metric. And so then the nice thing about this now is hopefully that you see is that, okay, so d sub p is a metric. There's some conditions, but now we can do Monte Carlo estimation because we're averaging. And so, okay, I mean, this is just a very complicated expression, but it's literally just a Monte Carlo estimator. And so here's my final, and I know that this is a disgusting estimate in a math department, but if I set the number of critics over which I'm going to average to 1, then this is a one-sample Monte Carlo. Like this scoring is a one-sample Monte Carlo estimate of this D1 metric. Okay, and so one final curious thing to note is that when I pick my stochastic process to be a Gaussian process, then the p equals 2 case of this metric, it corresponds to the maximum discrepancy over the same RKHS over which the Gaussian process is defined. Okay, so this is the the fix to that one, my claimed fix anyways to this single score assessment issue. I thought about this, but not too hard. So maybe yes, but that would be quite interesting to check. I did when I defined it, I did think, okay, like, is there an easy way to see this? I didn't immediately see it, and then I had other things to do. But it would be an interesting question to answer for sure. Okay, and just to finish off, so what were the contributions of this work? So we propose this formal definition of accuracy and naturalness, extended this theory from this called distortion perception theory to translation by the addition of this, like, it's maybe not a huge generalization, but it's practically interesting. We showed that the trade-off must exist in practice as well. Had a look at, okay, what are the current systems like? And showed this connection between no reference metric. So no reference metric is this one that just purely looks at a candidate and statistical distances. And so the message of the talk is that you cannot feed two birds with one score. Yeah, any questions, comments, please tear into me. Mm-hmm.
I'm not sure. I mean, is this trade-off really existing, or it is on how we formalize, how we measure naturalness? Because I mean, if you come back to the German example, right?
Mm-hmm.
One could argue that is spoken German, the most accurate one was the one that most of the people would use, while maybe in written form of German, one would have picked more the philosophical, like, one, right?
Yeah.
And both of them, I mean, it feels that we are measuring them as two independent factors, and in general, what you would like to have is condition on accuracy, how natural I sound, or how context, because, I mean, you call it naturalness, but it feels a bit like contextual. I mean, in some context, one of them would fit better than others.
Mm-hmm.
So can you comment on this? I mean, is it really a trade-off that exists in the reality, or is it on how we measure? And I'm asking mostly because, for example, in the fairness community, machine learning, we have seen these kind of problems already.
Mm-hmm.
And sometimes some of these trade-offs appear on how we operationalize these concepts
Absolutely.
rather than they exist. And also when you had the Spanish, I mean, you pick up on 3 languages that I speak, right? And you were going very close to the utopia point.
Yes.
Which means that it's more on maybe the family class. I mean, Spanish and English are 2 out of the 3 most spoken languages in the world. So
Yeah. Yeah, sure. So you're absolutely right. Of course, like, to start with the baseline, like, of course, it really depends on like, all these results, they depend on how you define like accuracy and naturalness. And so I'm not claiming that our notion of naturalness is the ultimate. It's just something that, so it comes from, like, my area of expertise. And so this notion of naturalness is actually quite widely accepted now in data compression. So where data compression, like, what you care about is that the output of a compressor, it looks good. It looks photorealistic or whatever. And so it's just something that some people have already agreed on that is a good idea, and it's something that can be analyzed. Like, the starting point, like, I'm certainly not claiming that, yeah, this theory is the ultimate, like non plus ultra, but previously to this work, there was nothing. Like, people, like, as I said, like, obviously everyone has some, like, internal notion of accuracy and naturalness, what that should mean, but then, like, we cannot study, like, just some intuitive notion. So this is just one way of formalizing it. And then the other point, so yes, you are right. So this goes back to this question of, okay, does perfect accuracy imply perfect naturalness? So there's sort of like a trivial, but I would claim pathological counterexample to our setup where perfect naturalness, perfect accuracy can imply perfect naturalness, where you define the reference distribution to be the output distribution of a perfectly accurate translation system. So you're allowed to make this definition, and then that's very clearly going to be both perfectly accurate and perfectly natural. The reason why it's I say that it's no in our setup is more a philosophical one. It's more a thesis than, you know, than a theorem, in the sense that what we want is to exclude dependence of the notion of naturalness in one language on another language. So this is just to say that any notion, any sensible notion within translation of naturalness in German should not depend on English or Spanish or Japanese or whatever else. And so if you exclude that, then you can no longer get this. Okay, and to finally get to your point about this colloquial versus written, so this is actually a feature and not a bug of our theory, because it all hinges on what you pick for the reference distribution. So if you're writing a chatbot where it's fine to be more colloquial, then you would ideally pick a reference distribution that has colloquial speech more represented than the formal. And if you want scientific writing or newspaper writing LLMs, which is a bit dystopian, but whatever, then you would pick the reference distribution to be a little bit more aligned with that. So it's another thing that it's, you know, in hindsight, it's maybe like so obvious that like you ask, okay, what's the point of even saying this? But it turns out, at least that the Google Translate team, I hope they are not too mad for me saying this, but they didn't even realize that, okay, you can pick different reference distributions. Obviously, they know that you can guide the output of a translation system by picking the data set, but they have never explicitly sort of written down this notion that you can pick different references. So this is just something that maybe for you is like, it's simple to see, but for practitioners, this was an interesting insight.
I see a lot of steps on the machine learning community that we tend to overlook. Some of the things that I think formalizing is always a good step.
Yeah.
I guess I was more going on the direction of coming back to the title of your talk, right?
Mm-hmm.
I mean, is it that there is no perfect metric, right? Because in the sense that, first of all, we are in language, which is very context dependent. Second, you have a reference, and of course, if you translate the reference source or the reference distribution, for example, from Spanish from Spain versus from Spanish from South America, each country would be different, right? And I was wondering if actually the problem comes from optimizing for one metric, and whether we might not get simply more robust models if we would optimize for more than one, like the more the merrier.
Yeah.
It feels that your work is going a bit in that direction, that because all the metrics seems to be proxies, imperfect proxies, if you collect enough of these proxies and you try to evaluate or optimize for several of them, you might actually be able to push the boundaries than only looking at one edge, one of the axes in your optimization. But that is a bit too.
Yeah, and so there is work on that. So you can show that if you optimize systems. So just to be clear, this work is about evaluation purely, not about optimization. So this just shows that basically, no matter how you pick your two, like you pick an accuracy metric and this naturalness metric, then you'll get a trade-off. But you're totally right that if you pick like very, very good metrics, so maybe they are this combination of like multiple proxies, then you'll get something that, you know, maybe captures better what you actually want to do. So there is some work where there was this one guy who optimized some translation system for, I think, like 10 different, like a weighted average of 10 different like accuracy metrics, some of them neural, some of them pure accuracy, like this charf, and then did a human evaluation on the output, and humans, you know, liked it better than if you just measured that. I mean, it all comes back to you know, like actually saying what you want to measure is very, very hard. And so you're totally right. Like if you pick something that is like maybe captures perfectly what you want, then maybe you should just evaluate according to that. This is more like, this work is mainly aimed at, like, the goal that I hope it will achieve is that translation people will just realize that, you know, just chasing this, blindly chasing this idea of like, we'll find one metric that is going to solve everything, is going to be, because this is the feeling, is hopeless. I don't know if I answered your question properly.
The risk of this kind of work is that we might enter into these trade-offs, problems that we believe they are compromising a lot, and some of these trade-offs might be a bit artificial at times.
Sure. I fully agree with that. Yeah, absolutely.
Yeah, we have a tendency to go into technical solutionism where we believe that, yeah, if there is a trade-off, this trade-off exists in reality, while not necessarily always the case, and we forget that there is a context in language which is very prominent.
Absolutely, you're totally right. And you could even say like here, like you can maybe even see just a final moment, like you can see here that for the accuracy metric, this MSE idea, like you get a lot more like factor clusters, whereas when we're looking at Comet, which is this metric that is supposed to assess accuracy and naturalness jointly, you see like correlation for much longer, whatever that means. Like they're much like this cluster is a lot more linear here. Our point really is that I already agree with what you're saying, that ultimately the trade-off matters on what metric you pick. So if you pick a very, very good metric, maybe this trade-off is not going to be as severe. So does it matter practically or not? We don't know yet, but for sure there's this tension. I mean, I think we're already in agreement about this. But yeah. Thank you.